These examples go with Lesson 1.3, Functions and Relations. Example 1. For the table shown, A, write the set of ordered pairs that defines the relation, B, write the domain, and C, write the range. Okay, for part A, the ordered pairs which define the relation will be positive 3, which goes with negative 4, and negative 2, which is paired with 0, and positive 5, which is paired with positive 3, and positive 1, which is paired with 0. For part B, the domain, this is the set of all the x values. In this case, it's just going to be my top row. So negative 2, positive 1, positive 3, positive 5. Now we normally list these in increasing order, but it's not wrong not to. It just kind of makes it easier to grade. Part C is asking us to list the range. This is just the set of y values in our ordered pairs. In this case, it'll be the bottom row. And the range consists of negative 4, 0, and positive 3. So when an element repeats itself like 0 did, we only have to list it the one time as being in the range. Example 2. Determine if the relation defines y as a function of x. Probably the best way to do this is to do a mapping. Okay, so what I'm going to do for part A is I'm going to list the domain, which is positive 3, positive 5, and positive 8 in one oval. And then I'm going to list the range, which is negative 1 and positive 4 in another oval. And now I'm going to match up each element in the domain with the element it goes with in the range. And if anything over here in the domain has two arrows coming from it, we'll know it's not a function. But as long as there's only one arrow coming out of every number here in the domain, we're okay and we have a function. All right, so 8 is paired with 4, like this. 3 is paired with negative 1, like so. And 5 is paired with 4, like this. So this one is a function of y, or a function of x. For B, I'm going to do the same thing. I'm going to list my domain elements in an oval, and that's going to give me negative 3, positive 1, and positive 9. Here's my domain elements. And then my range elements are going to be 0, 1, 2, and 5. And now I'm going to draw arrows that pair up my domain elements to the range. So negative 3 pairs with positive 2. Positive 9 pairs with 5. Positive 1 pairs with 0. And then negative 3 pairs with 0. Now, I notice over here in my domain, negative 3 has two arrows coming from it. So this one, not a function, because one of my domain elements goes to two different range elements. Example 3. Determine if the graph of the relation is a function. We're trying to see if the function passes the vertical line test. Now remember, the vertical line test just means, can I draw a vertical line anywhere on the graph paper that's going to intersect my function more than once? Well, here, I can see I can draw a vertical line right here that intersects in this place and this place. So automatically I know this is not a function. Now you know there are several other places where I could have drawn my vertical line that would intersect in more than one spot, but we only have to find one vertical line that intersects our graph in more than one place to say that it's not a function. And sometimes there may only be one vertical line that causes it not to be a function. All right, for B, It looks like I can draw my vertical line here. I'm okay. Here I'm okay. Here I'm okay. I think this one's going to be okay. We're not going to be able to find any vertical line that's going to cross the graph more than once. So this one is a function. All right, for C, looks like back here I'm okay. I have a function, and when I move over here, I'm okay. I still have a function. So the only place where I'm in question is right here. And this dot is actually closed. This one down here, the picture doesn't make it very clear, but this dot is open. And since it's open, this one is going to be a function that's not going to fail the vertical line test because one of them is closed and one of them is open. If it were closed, it would fail, and this would not be a function. Example 4. Evaluate h of x is equal to 4x minus 3 for the given values. Well, for part A, h of negative 3 is going to be 4 times negative 3 minus 3. 4 times negative 3 is negative 12, and negative 12 minus 3 is going to give me negative 15. H of negative 1, this is going to be 4 times negative 1 minus 3. 4 times negative 1 is negative 4. Negative 4 minus 3 is negative 7. H of 0 is going to be 4 times 0 minus 3. So 4 times 0 is 0. 0 minus 3, negative 3. H of 1 is going to be 4 times positive 1 minus 3. 4 times 1 is 4, and 4 minus 3 is 1. And then h of 3 is going to be 4 times 3 minus 3. Well, 4 times 3 is 12, and 12 minus 3 is 9. Example 5. This is going to be a different kind of substitution. We're going to evaluate f of x is equal to the opposite of x squared plus 4x for the given values. Now the first one, we're going to do f of t. Well, f of t just means we're going to take all the x's out right here and here and here, and we're going to replace them with t's. So we're going to have the opposite of t squared plus 4 times t. And we're done. B is going to be a little bit trickier because instead of replacing just one variable, we're going to replace 2. So all the x's we're going to replace here with a plus h. All right, that's going to give us the opposite of a plus h squared, because the function is squared, plus 4 times, and not 4 times x, but 4 times a plus h. All right, let's expand this. A plus h squared is actually a plus h times a plus h. And let's distribute the 4 in the parentheses. We've got 4a plus 4h. Over here, we're going to have a squared plus ah plus ha plus h squared. All right, we'll add our like terms together right here. This is going to give us the opposite of a squared plus 2h's plus h squared plus 4a plus 4h. And finally, what we'll do is we'll take that negative and we'll distribute it into the parentheses. So we've got negative a squared minus 2ha minus h squared plus 4a plus 4h. And if there were any like terms here Now would be the time to combine them, but there aren't any, so we're finished. Example 6. We are to determine the domain and the range for the functions shown in the graphs below. Alright, remember, the domain is just the list of the x values, and the range is the list of the y values. Now for A, we just have a set of points. So when I do my domain, I'm just going to have some x values listed. I'm not going to have to do this in interval notation. And normally when we do domain and range, we start, well, domain, we'll start the furthest to the left. So that means I'm going to start with this point right here, where x is equal to -4. And then I'm going to move to this one right here, where x is equal to -2. And then we'll move to this one where x is equal to 0. And then we'll move to this point right here where x is equal to +3. And finally, we'll pick this one up right here where x is equal to +4. So there's our domain. Now for the range, I'll generally work my way from the bottom up. So the lowest point on the graph is this one. And here, the y is equal to -3. All right, moving up, y is equal to 0. Moving up to the next one, y is equal to 1. And then I have another one that's equal to 1, but I don't have to write that one in there. So this is the last one we're going to pick up. Y is going to be equal to 5. B is going to be a little bit trickier, but we're just going to write this in interval notation because we're not going to be able to list out every element of the domain and the range like we could here because we have more than just points. We've connected those points with lines and line segments. And we want to be sure and include everything that's in between the points that we have marked on here. Okay, for the domain, I noticed that there is an arrow on the end of this. And so that means this is forever going to be moving up and to the left. And since the arrow is on here, that means that the domain is going to go all the way back to -infinity. There is no leftmost point on this graph because of that arrow. All right, then if I look to the right, the furthest to the right the graph can go on the x-axis is right here because past here there is no graph. And at this point, x is equal to +4. So infinity never has a bracket. And the +4 is going to get a bracket because that circle right there is closed. All right, now from the range is going to go from the lowest point on the graph to the highest point on the graph. Well, the lowest point is at this place right here. And again, we're going to write this as an interval so that we can include all the points in between our dots here. All right, so at this point, the lowest point, y is actually equal to +4 again. Yeah, -4. And then the highest point on the graph, well, this is the highest point that I've labeled, but if I follow this, I notice that the arrow has been shaded in here. Now remember, this arrow means the graph is forever going to the left and up, which means that since it's going up forever, there is no highest point. And so this graph is actually going toward +infinity. The -4 is going to get a bracket because there's a closed circle down here, and then infinity always gets a parentheses. To find the domain of a function based on its equation, we're going to follow the rule that the domain for any function is all real numbers unless we have a variable in the denominator or a square root somewhere in the problem. Example 7 is asking us to write the domain for each function in interval notation. Okay, let's look at A. Part A actually has a variable down here in the denominator. Okay, so in order to find the domain for this function, I need to take the denominator and I need to set it equal to 0, because whatever answer I get here is going to tell me what cannot be in the domain, because we do not want to be dividing by 0. All right, so let's subtract by 1. That gives me 3x equal to 1. And then when I divide both sides by 3, x equals 1/3. This one is not in the domain. And the reason it's not in the domain is because it causes me to be dividing by 0. When I plug, sorry, this should be negative 1/3. When I plug in negative 1/3 here, this gives me negative 1. Negative 1 plus 1 is 0. I'm dividing by 0. That's a no-no. Okay. All right. If we want to see the picture of the domain, all right, the domain is going to be everything except for negative 1/3. Well, smaller than negative 1/3 is negative 2/3. Bigger than negative 1/3 is going to be 0. Okay. We do not want to include negative 1/3, but everything else is okay to include. And so in interval notation, everything except for negative 1/3 would go from negative infinity to negative 1/3 union, and then it's going to go from negative 1/3 to positive infinity. And be sure you have parentheses around both of these. Part B, g of x is equal to x squared divided by 5. This is a nice one because if we follow our rule, the first rule is, the domain of any function is all real numbers, unless we have a variable in the denominator. We have a denominator with no variable, so okay there, or a square root somewhere in the problem. There's no radical here, so we automatically know this one's going to be all real numbers. And the way we write all real numbers in interval notation is negative infinity to positive infinity. Part C, k of x is equal to the square root of x plus 3. I have a radical in the problem here. Now to find the domain, I'm going to take the inside of the radical right here, and I'm going to set it greater than or equal to 0, because taking the square root of 0 is okay, but taking the square root of anything less than 0 or a negative number is not okay. It's not a real number. And whatever I get when I solve this inequality is going to be my domain. Well, let's subtract 3 from both sides. We have x is greater than or equal to negative 3. This is the domain. If we want to look at a picture of this, we've got negative 3. Smaller than negative 3 is negative 4. Bigger than negative 3 is negative 2. We'll have a closed circle at negative 3. And then everything greater than that is going to be to the right. Right? So interval notation for part C is going to go from bracket negative 3 to positive infinity with a parenthesis. All right, part D. P of x is equal to 2x squared plus 3x. There's no denominator with a variable. There's no radical in the problem here at all. Once again, this is going to be all real numbers, negative infinity to positive infinity. And that does it. All right, in example 8, we're going to use the function in the picture to find the following pieces. For part A, we want to know f of negative 2. In other words, when x is equal to negative 2, what is y equal to? Well, let's see. There's -1. There's -2. When x is equal to -2, here's my point on the function. It looks like y is going to be equal to +1 because the point -2, +1 falls on that black line right there. Part B, f of +4. So when x is equal to 4, what is y equal to? Let's find out. 1, 2, 3, 4. We follow the graph down. I come to this open circle right here. That means that there is no y value that goes with 4 because 4 is not included in the domain. So this one is undefined. All right, part C. Now we're going to kind of do the opposite of that. Now I'm going to tell you what y is equal to. Remember, f of x, we can just think of that as y. So what does x look like when y is equal to 3? So let's find y equals 3. 1, 2, 3. We'll follow it back over here. If that's this point right here, what is x equal to at this point? 1, 2, 3, -4. All right. Now we're looking for x whenever f of x is equal to 1. Now, if we just treat this like a y, when y is equal to 1, what is x equal to? Well, let's see. Y is equal to 1 right here. That starts at this point right here because that's equal to 1. This point, y is equal to 1. And everything in between here, y is equal to 1. So there's actually an interval here where x is equal to 1. And that occurs from -3 to -1. And we're going to put brackets on there because -3 goes with +1 and -1 goes with positive. Sorry, there should be positive ones. All right, E, the x-intercept. Where does the graph cross the x-axis? Well, here's the x-axis. Here's the graph crossing. It crosses right here. So it crosses at 0, 0. What about the y-intercept? Where does the graph cross the y-axis? Here's the y-axis. Here's my picture crossing the y-axis. Again, it crosses at 0, 0. Okay, now for the domain of f. We look on this end of the graph and we see that there is actually an arrow here indicating that the graph is going up and to the left forever. That means there is no furthest to the left that we can go, so the domain is going to start -infinity. And if we look to the right, the furthest to the right the graph can go, this is the last point right here. We can't go any further than that. There's no graph. And that point we said was represented by +4. Since there's an open circle there, we're going to need to put a parentheses around this, and then infinity, of course, is going to need a parentheses as well. All right, for the range, now we're reading from the bottommost point up. The furthest down the graph goes is right here, and at this point, y is equal to 1, 2, 3, -4. And then the furthest up it can go, well, again, I look over here and I see that this arrow has been shaded in, and so it actually goes on forever up and to the left, which means that our range is going to +infinity. This is going to get a parentheses, and because of that open circle down there, the -4 is going to get a parentheses as well.